and welcome to this STM32F334 Getting Started video. The STM32F334 microcontroller is optimized for digital power applications such as DSMPS, lighting, welding, inverters for solar systems, and wireless chargers. The STM32F334 embeds an ARM Cortex-M4 core running at 72 MHz, providing up to 90 DMIPS with routine booster, CCM SRAM. Guaranteed high-resolution PWM timer at 217 picoseconds accuracy with a number of features to offload the CPU. Built-in analog for protection, control, and signal conditioning. Fast 5 megasamples per second analog to digital converter. Operational amplifier with built-in gain, fast comparators, digital to analog converters, and extended connectivity thanks to USART, I2C, CAN, and SPI peripherals. Let's now operate the STM32F334 Discovery. First, connect the board to a PC. The 4 LEDs should start sequentially blinking until the user button is pushed. The first application mode activates the automatic dimming sequence. Press the button again to make the power LED start blinking. Press the button again to exit LED strobe mode and enter manual dimming mode. A long press on the user button successively increases or decreases the intensity of the power LED after each release. Press the button again to exit manual LED dimming mode. We are now going to see an example of a waveform generated by the STM32F334. The output waveform on TP3 shows the advantage of the high-resolution timer versus a standard timer. Rising slope steps of the filtered PWM are visible with a standard resolution timer. On falling slopes, the steps are not visible thanks to the high-resolution timer. Now let's explore the buck converter signals used to control the LED dimming. This video does not cover the buck boost function of the board. The signals that we are going to monitor are the buck drive, the buck sense feedback loop to the MCU's embedded comparator for regulation, and the reference signal of the internal comparator generated by the digital to analog embedded converter. The buck converter is used to load the power LED at a constant current. The LED brightness is adjusted by setting a number of 250 kHz burst drive pulses within a period of 400 Hz, not visible thanks to retinal persistence. Let's now see in detail the buck regulation sequence. During phase 1, the drive transistor is closed and the current through the LED is loading the inductor L2 until the sense voltage reflecting the image of the LED current reaches the comparator reference generated by the DAC. Then the drive transistor is opened, and during phase 2, inductor L2 discharges through the LED. After a 250 kHz period, phase 1 starts again. An interesting point to focus on is the reason why the comparator reference is not constant. The slope compensation is done to remove current mode convert subharmonic oscillations. Without the slope compensation, the signal waveform would be unstable, as shown at the bottom scope record. Another trick of the demo is the soft start and stop implementation for a more progressive LED brightness adjustment. We can see here that the LED brightness is controlled through its nominal current adjustment set by the comparator reference voltage. For more details about the STM32F334 Discovery Kit and related applications, please read user manuals UM1733, UM1735, UM1736, and UM1746, and application notes AN4539, AN4449, and AN4885. Application note AN4539 is a cookbook that comes with a collection of ready-to-use code examples. All this material is available at st.com/stm32 and st.com/stm32f3. Thank you for watching this video.